Hey, in this video we're going to be talking about some basic matrix transformation math. So the first real question is, why matrices? Why do we have to put up with these things? So the reason is that a matrix is one single structure that we can use and one operation that can apply to lots of different effects. All sorts of effects that we can imagine, all sorts of transforms. With that one operation, these different transforms can be composed together. And so it would be kind of a mess if we had to use multiple different data structures or ways to hold information and multiple operations in order to combine them. But with matrices, we have one compact representation of a transform, whether it be a scaling transform, a rotation, a translation, or something else entirely. And then we can combine it with any other matrix just by multiplying them in a special way. So this gives us some real flexibility because we don't need to know what a transform is going to do to an object in order to apply it to that object. We just have to multiply, and that makes it great. So let's first start looking at how do we apply a matrix to a vector in order to change it, in order to apply a transform to a vector. So let's say we have a matrix, so this is just any old transform. Let's make this a really simple one. So let's do the identity matrix in 3 dimensions. So 3 dimensions here means that I'm going to have 3 rows and 3 columns. This is a 3 by 3 matrix. And the identity matrix has 1s along the main diagonal. 1, 1, 1. And so when we multiply this by something, we expect that we're going to get the same thing out. It's not going to modify anything. So the identity matrix acts sort of as like a basis, sort of like a foundation for constructing other transforms. So we can start from the identity matrix and build on top of that and work through. This can be like no transform has been applied yet, but then we can collect transforms, combine them into this matrix, and apply them all at once. So if I take this matrix and I want to multiply it by a vector, we need a vector that has, let's say, 3 components because of a 3D vector. And when I multiply these, I'm going to get, hopefully, a vector out of it that is exactly the same. Nothing should have changed. So now let's go through the process of how this works. We want to generally, when we multiply, we are multiplying the each of the rows by this column vector in sequence. So let me rewrite this. Those are zeros. Alright, now let me actually do the math for it. So the first row of the matrix is 1, 0, 0. And the column vector is never going to change. It's x, y, and z. So we want to match up these first terms, the first elements. The 1 is multiplied by the x, so 1 times x. And then we're going to add to that 0 times the y. So the next elements, the next one from the row and the next one from this column vector. 0 times y. Plus the third ones, 0 and z, so 0 times z. On the next row, moving down to the next row is going to give us the next row of our answer. So 0 times x plus 1 times y plus 0 times z, making them all match like that. Moving down again into the last row, 0, 0, 1, we get 0x, 0y, and 1z. Alright? And then if we just add these all together, the zeros are just going to destroy these terms. So we end up with x, y, and z in the end. All right, let's apply that to a slightly different matrix and see what happens. So let's try a matrix like this. 2, 3, 1. And then the rest are zeros. So here I've adjusted our identity matrix so that it has a different number along the diagonal. Let me multiply that by our xyz vector. And what do we get? We get 2 times x plus 0 times y plus 0 times z, so I'm just going to leave those off. The next row is going to give me 0 times x, 3 times y, and 0 times z. All right. And then the last row, 0 times x, 0 times y, 1 times z. So we end up with this vector. I'm going to rewrite it just a little bit to clean it up. 2x, 3y, and I can just write z here. Okay. So what we've done here is we've just multiplied these numbers through, and the way it worked out is that the 2 went with the x, the 3 went with the y, and the 1 went with the z. This is a scaling matrix. We have applied different scales, 2, 3, and 1, to each of these dimensions. If this were like the vertex of a cube, and I applied the scaling matrix to every vertex of this cube, it would no longer be a cube. Each of those coordinates would be stretched out in the x and the y direction and stay where they are in the z direction. So it would become a kind of rectangular prism instead of a cube. And it'd be longest in the y dimension. Alright, so we have identity and scaling matrices. And for scaling matrices, if you want to modify these scaling factors, you just change the 2, change the 3, change the 1, or parameterize them, replace them with variables, and use those as your input. Okay, so let's talk about rotation. Let's get into that. Rotation. So the simplest rotations are done about one axis, let's say in 3 dimensions. And if you figure that out, if you put together rotations about one axis, they're kind of like 2-dimensional rotations anyway. So if you understand 2-dimensional rotations, applying them to 3 dimensions is no different. We just then go on and we combine rotations in order to rotate in different ways, and that's essentially how Euler angles are specified. So let's look at let's look at one of those rotation matrices. So if I wanted to rotate about the x-axis a certain angle, I would need some sort of matrix that ends up modifying my x, y, and z. Actually, let me not write it there yet. I want this matrix to multiply by my x, y, z. And in the end, I'm going to end up with a rotated x, y, and z. So if this were done in just 2 dimensions, you may have seen this before. What I want to end up with is something like x cosine of the angle minus y sine of the angle, x sine of the angle plus y cosine of the angle. So this is, I'm just pulling this out of thin air here, but this is how you would rotate in 2 dimensions if you didn't have a z coordinate. So if I wanted to rotate in 2 dimensions without a z coordinate, what I would want to do is end up with this kind of math in the end for the 2 coordinates I am rotating in. So if I'm rotating about the x-axis, then the two coordinates that are going to change are going to be the y and the z coordinates. So I could use this idea from our identity matrix. If this is 1, and this is 0, and this is 0, and then on each of the rows we have zeros in that x column, then when we multiply by x, y, and z, we're going to end up with the same x. Our x is not going to change. What we're aiming here to do is rotate in the plane that is in the y and z axes. So it ends up looking a lot like this two-dimensional rotation. We have a cosine term here, or element here, negative sine. That's a little messy. Let me rewrite that. Negative sine. We have sine here and cosine here. All right, so now when I multiply this through, let me go through the math of that with x, y, and z. All right, let's multiply it. So we end up with our x, 1 times our x, great. 0 times our y, 0 times our z, fine. On the next row of our answer, our resulting vector, we'll get 0 times our x, so the x component is not part of this rotation. We get y times the cosine, and we get z times the negative sine, so plus a negative z times the sine, right? And then for the last row, 0 times the x, and then y times sine, and z times cosine. Y sine plus z cosine. And that looks very similar to what we had for our two-dimensional rotation, except this one is in 3 dimensions about the x-axis. So let's look at the other two, rotation about the y-axis. This one is going to still look similar, except we want the y-coordinate to stay the same. So let's apply that part of the identity matrix. And in the corners, you're going to see the kind of rotation terms that we had before. Sine and cosine in a special order. So that when you multiply these out, you get the same kind of rotation, but just in a different plane. We're rotating about the y-axis, so this is the xz plane that we're rotating in. And then the rotation about the z-coordinate, the z-axis, is similar, except the z is where we want things to not change. And then our little two-dimensional rotation matrix shows up in this corner. Okay, just like that. So now when we apply these to any vector, we can rotate that vector in essentially 3-dimensional space. But we would like to also be able to apply these multiple rotations so that we can rotate in different dimensions all at the same time, composing those 3D transformations. So to do that, we're going to need an operation for multiplying matrices together. We have one for multiplying a matrix times a vector. We will need one for a matrix times a matrix. So let's say I have two matrices. Let's label them A and B, and we want to multiply them together. We're going to have two matrices. I'll label their elements A1, A2, A3, A4, A5, A6, and so on. That's a 7. we want to multiply by b. So let me give this a few terms. Alright, we're going to figure out how to multiply these. I'm going to follow the exact same pattern that I did for multiplying by a vector. We're going to be multiplying each row by each column. And as we change our row, we're changing the row of our answer. And as we change our column, so the column in the second one that we're considering, then we're changing the column of our answer. So let's do all of that out. It's going to be big. So we're going to multiply A1 times B1. We're going to add the next part. So A2 times B4. Alright, those are the ones that match up. A3 matches up with B7. So A3, B7. Alright, I'm drawing those 7s like 2s. Alright. Now we're going to go, let's say, down one row. A4 matching with B1. A5 matching with B4. And A6 matching with B7. Alright. Now we'll go down one more row to finish this part of it off. This is A7, A8, and A9 matched up with B1, B4, B7. So A7, doing it again. B1, A8, B4, and A9, B7. Okay, so that is the first column. If this were just a vector, I'd be done. But I need to go on for these other two columns that are essentially another two vectors that I need to do this for. So it takes a lot of writing, but let's do it. We're now considering the second column, so A1 times B2 plus A2 times B5 plus A3 times B8. Alright, those same B values are going to show up in the next one when I move down one row. A4, B2, A5, B5, A3, not A3, A6, B8. And then down one more row, sticking with the same middle vector here, middle column. So A7, A7, B2, A8, B5, A9, B8. Great. So let me make sure everything lines up. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, just double checking. Looks all good so far. And then for the last column, we're going to have to do it again. So we've got A1, B3 plus A2, B6 plus A3, B9. Right? Going down, we've got A4, B3, A5, B6, A6, B9. And then down one more row, A7, B3, A8, B6, and A9, B9. Okay, look at that monster. Alright, so we now have a full expression for this multiplication. Now, thankfully, we don't usually have to go through all of this work. We can rely on our computer to do all of this multiplication and addition, but the important point is it doesn't matter if A is a rotation and B is a scale or a translation or some other combination of matrices. We just blindly perform this operation and we get an answer that is consistent and that we can apply to a vector in order to transform it. That's great. That's really great. So when we do when we want to transform something, a vector, by convention, we do what's called left multiplication. We want to multiply on the left. So if I write it out as, say, an operation A, some transform A, and I want to multiply by V, I write it out this way, applying that transform to V. If I wanted to do another operation on top of this, let's say the operation B, then I would put that on the left. So this is first multiplying A times V, and then multiplying B times that answer. You could think of it the other way. You could say, oh, well, maybe we're multiplying these matrices together first, and then we're applying that result to the vector. And that's totally fine too. Those are equivalent. But what is different is if you write it A, B, V. This is not the same. So this generally is not the same. B times A times V is not A times B times V. There are some cases where that is true, where they are equal to each other, but generally matrix multiplication is not commutative. That means you cannot just switch around terms in this operation. So like if you're multiplying scalars like 5 times 6, that's the same as 6 times 5, but not when it comes to matrices. You cannot just switch matrices and expect it to come out with the same answer. As like a tangible example, let's say you have a coordinate system and you have an object. Here's my object, and I want to rotate and translate it. So spin it and move it. So let's say I do a rotation first. We rotate, so now I'm like this, and then I translate and move it over to the side here. So let me just draw a dashed version of it. Great. That would work fine. But now let's say I wanted to do the opposite order. So let's say I wanted to translate first. Let's take this object, oops, it's a square first. Start off as a square, move it over, and then when I go to rotate it, well, the rotation is going to act differently. Let's say I were intending to rotate it about this point. That would mean my rotation would make this object move up here, and I'd end up with a rotated square, but it would be in the wrong position, or a different position, a different final position than it originally had. And so this order of operation matters immensely. Okay, so let's look at our last one. We looked at identity and scaling and rotation. So let's look at translation. Alright, so translation is reasonably simple. We just want to take our vector, right? We have a vector x, y, z, and we want to transform it so that it is now x plus, let's say, delta x, y plus delta y, z plus delta z. That's what we want to achieve. So we have just these three parameters, how much you want to move it in the x, y, and z dimensions, and we just want to add those in. Now adding them is really easy. However, we're not doing adding as our operation here. We are multiplying matrices. So let's see. Let's look at that matrix multiplication here. It's very complicated, but we're trying to see now, is there a way that we could add in a particular term? And if you look at all of these, they're all mixed together. So a times b, a times b, a times b. So if I set up a matrix that had a translation, I would have to kind of ignore one of these a components in order to make that work. Put another way, we cannot do just a simple multiplication of 3 by 3 matrices and arrive at a translation. It's just not going to work. It doesn't matter how I put these in here. Let's start with an identity matrix. We know that some of these terms are going to represent like scaling along the diagonal. Rotation, if you do like several of them and you do them with an angle. So if I just changed one of these and was like, okay, well, what does this do? Let's call it a Q, right? We're going to end up with a matrix or a vector. Let's multiply through, where we have x plus qz, y, and z, right? So the problem here, as I pointed out in the more complicated looking one, is that we're mixing components. You have x plus something times z. So the z coordinate of this original vector is going to change your x coordinate. That's not a translation. I want only this thing that I'm trying to add to it getting added in, nothing with z. That just throws a wrench in it. So there is a trick to this, but it requires, well, unfortunately, a few more operations. The trick is we expand this. Instead of working with 3 dimensions and then being like, oh, well, we have to kind of ignore the z, let's go to 4 dimensions. Let's do a 4 by 4 matrix. Here's a 4 by 4 identity matrix. Right? And let's multiply that by a 4 vector, x, y, z, and then let's just call this this last one w, but you can usually just replace it with a 1. So let's just leave it here for now, and we can then, if we treat w as 1, then we can go ahead and we can have some sort of mixture where we have x plus some number, let's say delta x times w, y plus delta y times w, z plus delta z times w, and we'll end up with something for w as well, but let's just ignore that for now. So I'll leave it there, but let me think about how this is going to work. So we want something that's going to multiply each of these by w, and if we follow through with our math, x times, or 1 times x, 0 times z, or 0 times y, 0 times z, and then this times the w. So in our first one, I want this to be delta x. Our second one, I'm going to want delta y there, delta z here, and then this is going to work out. Our last row here, 0, 0, 0, 1, is going to cancel everything out except for w, and that's what we're going to end up with. Now, if we just let w be 1, then that's our translation matrix. We've done it. It's a little annoying that we have to go into 4 dimensions in order to apply a 3-dimensional transformation. But this is the easiest way to do it with matrix multiplication. It also gives us the tools to express the idea of infinity in this, and we'll talk about that further when we talk about projections. But for now, this gives us the tools we need. We're going to have to extend our other matrices by just adding another row 0, 0, 0, 1 and another column 0, 0, 0, 1 to all of our matrices so far, but they work exactly the same otherwise. So that's great. That gets us there. We now have the math that we need to express scaling, rotation, translation, and applying them as matrices and doing operations in that way. So those are the basic transforms, and we'll be talking further about how this knowledge applies to more complex transforms like projection matrices, when you're trying to flatten an image onto a screen, or when you're trying to fit a world inside a regular box. These things are really important for game development and 3D graphics. I'll see you then.